Hello students, welcome to EPG Pathshala. I am Dr. Jasjeet Kaur Narang from Khalsa College of Pharmacy, Khalsa University, Amritsar. Today we are going to discuss about a module, surface active agents under the paper Cosmetics. The objective of this module is to study about the surface active agents, humectants and the antioxidants. First we start with a basic introduction. Surfactants are necessary ingredients for the cosmetics, toiletries, as well as personal care products for enhancing their action as well as performance. Surfactants can be defined as the substances that are short-chain fatty acids having one part that has an affinity for the non-polar media and one part that has an affinity for the polar media. Surfactants are often used in dosage forms as emulsifying agents, solubilizing agents, suspensions, stabilizers, as well as wetting agents. The market of the cosmetic surfactants has grown extensively during the past few years. This could be attributed to the increased use of cosmetics associated with the improved living standards of people as well as the cultural shifts occurring worldwide. Majority of the surfactants used in cosmetics are derived from substances naturally present in the body and hence are safe for use. Dimeric surfactants are a class of low-cost modern surfactants which have been reported to have greater utility and versatility in the formulation of cosmetics as compared to the conventional surfactants. This is due to the lower critical micellar concentration, higher solubilizing capacity, and good aqueous solubility, as well as the antimicrobial activity which they possess, which is unique to them. Besides this, properties like ability to form foam and being very mild to the human skin enhances their application in the formulation of cleansers, both for facial use as well as for body use. Surfactants are made of two distinct portions, namely a polar head and a non-polar tail. When placed in the aqueous solvents, the surfactants at a concentration known as a critical micellar concentration orient themselves in such a way that their polar heads face their non-polar face. This orientation helps in decreasing the contact angle between the aqueous phase and the non-polar portion of the surfactant. This phenomena is known as micellization and the aggregates thus formed are termed micelles. The concentration of the surfactant decides the shape of these aggregates, which varies from laminar to cylindrical. This figure illustrates the structure of a normal surfactant. Classification of surfactants. There are four types of surfactants which can be classified as number 1, anionic. Anionic surfactants dissociate in water to give an amphiphilic anion and a cation, which is in general an alkaline metal or can be a quaternary ammonium compound. They are the most commonly used surfactants. Examples include sulfate, sulfonate, and ether sulfate. The second type of surfactants are cationic surfactants. These surfactants dissociate in water into an amphiphilic cation and an anion, most often of the halogen type. For example, the primary ammonium compounds and the secondary ammonium compounds. Non-ionic is the third category of surfactants. They do not ionize in aqueous solutions because of their hydrophilic group, and this hydrophilic group is non-dissociable type, such as alcohol, phenol, ether, ester, or amide. Examples of the non-ionic surfactant groups include polyoxyethylene, acetylenic group, monoethanolamine, and diethanolamine. The fourth and the last type of amphoteric surfactants, those surfactants which exhibit both the anionic as well as cationic dissociations. They are also known as zwitterions. This is the case of synthetic products like betanes or sulfobetanes and natural substances such as amino acids and phospholipids. For example, amino oxide, betamine, and amino carboxylate. The other type of surfactants, besides what we have discussed, include silicone surfactants. They consist of permethylated siloxane group coupled to one or more polar groups. The most common examples include polydimethylsiloxane, polyoxyalkyne, graft copolymers, but they also include smaller molecules like trisiloxane or superwetter surfactants. They are used in a wide range of applications in which the conventional hydrocarbon surfactants are quite ineffective. They are surface active in both aqueous and non-aqueous systems, and they lower the surface tension to values as low as 20 m per Newton meter. They are usually liquids even at high molecular weights. The trisiloxanes promote spreading of the aqueous formulations on hydrophobic surfaces such as polyethylene. Natural polysaccharides. The most important emulsifying agent in this group is acacia. This stabilizes the oil in water emulsions by forming a strong multi-molecular film around each oil globule, and so coalescence is retarded by the presence of a hydrophilic barrier between the oil phase and the aqueous phase. Phospholipids. Purified lecithins are natural surfactants derived from the egg yolk or from soybean oil. They are used extensively as oil-water emulsifiers, both in parenteral as well as oral emulsions. They are composed of complex mixtures of neutral and negatively charged phospholipids, of which the major components are phosphatidylcholine and phosphatidylethanolamine. Steroidal emulsifiers. Examples of steroidal emulsifying agents derived from the animal sources include wool fat, which is also known as lanolin, wool alcohol, beeswax, and cholesterol. They are generally complex mixtures of cholesterol, long-chain alcohols, and related sterols. Purified derivatives are still widely used in traditional dermatological emulsions such as creams, as water in oil emulsifiers, and for their emollient properties. They are prone to oxidation and hydrolysis, and antioxidants may need to be incorporated into the emulsion formulated using them. Humectants. Introduction. Humectants or moisturizers are compounds that induce moisturizing properties to the formulations, including those which are made for use on the skin. Humectants should never be confused with emollients. They are not emollients, which are mainly hydrocarbon compounds. These are mainly responsible for resisting any evaporation through the skin and therefore make the skin more soft and liable by keeping and retaining water in it. The main property of any compound to act as a humectant is that it should be in its ionized form and that it should be carrying charges, because the unionized substances do not act as humectants. Skin also contains some other natural humectants that include salts, urea, and proteins. One of the most important non-pharmaceutical use of humectants is that it retains the moisture in frozen foods. Therefore, it prevents it from drying as well as maintains the elegance and appearance of the processed foods. Types of humectants. Humectants can be of different types and are classified as: number 1, inorganic humectants. Their use is very less and limited in sun and cosmetic preparations because they are less compatible with most of the compounds and also have chances of causing corrosion. Calcium chloride is an example of an inorganic humectant used as a component of cosmetic products. The second type of humectants are metal organic humectants. These humectants have limited use in cosmetics because of their compatibility problems, their corrosive nature, and a pronounced taste. The example of metal organic humectants includes sodium lactate, which can be used in skin creams. The third type of humectants are the organic humectants. These are widely used in cosmetics. They include polyhydric alcohols, their esters, and ethers. The most commonly used organic humectants are glycerol, ethylene glycol, polyethylene glycol or PEG, diethylene glycol, and ethylene glycol. Choice of humectants. A humectant for use as a component of the cosmetic preparation should be economical, compatible, and very less reactive. It should be made from ethylene oxide and water under pressure in the presence of catalyst. The higher the E of partial pressure, the higher is the molecular weight of the humectant. So while choosing a humectant, the molecular weight has to be kept in mind. If the molecular weight is greater than 600, we get solid humectants like polyethylene glycols. If we are using a liquid polyethylene glycol, it is going to be very hygroscopic and not good for drugs which are degraded by moisture. Solid polyethylene glycols are not hygroscopic and for moisture sensitive drugs can be a good choice as humectants. Humectants in general should be non-irritant to the skin. They should absorb water from the air and retain the same under the natural conditions of the atmospheric humidity. It should not cause too much change only in the water content, as well as it should keep the relative humidity, it should keep the formulation resistant to any changes in the relative humidity and should remain within the normal humidity range. It should be compatible with a large number of raw materials. It should be colorless, or if it has a color, it should not be too intense. It should be non-toxic. It should be non-corrosive to the packaging materials, which are normally used for packaging the cosmetics. It should not solidify under normal conditions. Its viscosity and temperature curve should be relatively flatter. Unusual humectants. These include those humectants which are having some unusual applications. These include glyceryl triacetate, neo-agarobiols, sugar alcohols, or sugar polyols such as glycerol, sorbitol, xylitol, and malitol, polymeric polyols such as polydextrose, urea, urea, aloe vera gel, MP-diol, alpha hydroxy acids such as lactic acid, honey, lithium chloride, sodium hexametaphosphate, E452I. Special uses of surfactants. Besides their usual applications as a component of the cosmetic products, surfactants also have some special uses. Humectants are generally regarded as safe even for injectable products and by inference for all other products as well. Humectants can also bind and inactivate many actives, which includes drugs as well as preservatives. Humectants also show laxative effects when used in large amounts. Examples include high molecular weight polyethylene glycol or PEG and electrolytes, which are used to flush out the bowel before endoscopy or other internal examinations such as surgery. When it is used as a food additive, a humectant keeps the food moist as well as tasty. This maintains the freshness of the food and increases its acceptance among the customers. Besides the above uses, humectants are also used as a part of anti-static coating for plastics. Antioxidants. Introduction. An antioxidant can be defined as a substance that hinders the oxidation of a given substance. In the process of oxidation, there is the production of ROS or reactive oxygen species. This results in a continuity of chemical reactions during the propagation phase, which ultimately harms the body cells. Some substances, such as ascorbic acids, have the ability to hinder this chemical reaction and its propagation phase. These substances are known as antioxidants. In general, antioxidants also hinder origination of reactive oxygen species, besides hindering the propagation of chemical reaction. Antioxidants have secured a very respectable position in many fields of science, including medicine and in dermatological preparation. Classification of antioxidants. Antioxidants are classified as endogenous antioxidants, exogenous antioxidants. First, we take up the endogenous antioxidants. Endogenous antioxidants are basically enzymes that protect the body cells from the chemical oxidation reaction. The main function of these enzymes is to reduce the amount of oxidants, thereby inhibiting the reaction. The production of these enzymes depends on induction of the oxidative stress. A lot of variability is observed in the quantity of these antioxidants present between the different tissues and the cell types. Examples of endogenous antioxidants include catalase, hemioxygenase, etc. The second type of antioxidants are the exogenous antioxidants. As the name suggests, they are exogenous origin. That is, they are not synthesized within the body. Vitamins like vitamin E and vitamin C are examples of lipophilic and hydrophilic antioxidants with strong antioxidant activity. Vitamin E acts by inhibiting the peroxidation of lipids present in the biological membranes by forming a radical tocopherol, which results in termination of the chain reaction involved in the process of oxidation. Trace metals like selenium are used as cofactors for enhancing the antioxidant activity of vitamin E. Now we discuss the mechanism of action of antioxidants. There is a control operation in the living tissues that maintains a balance of the reactive oxygen species or ROS in the body. The production of ROS in the body triggers many endogenous antioxidants in the body to play their action against the oxidation reaction. Endogenous antioxidants are present in the body in sufficient amount, and their lack, if any, can be balanced by administering the exogenous antioxidants to protect the body cells. The mechanism of action of antioxidant mainly depends on the type of the ROS generated and the target site of origin of ROS. Direct scavenging of the free radicals, resulting in the reduction of free radicals in and around the body cells, hindering the free radicals from reaching their target tissues and cell, and terminating the chain reactions involved in the oxidation process are the few mechanisms responsible for the activity of antioxidants. Now we discuss the free radical theory of aging and the role of antioxidants. Reactive oxygen species, or ROS, an unavoidable end product of the aerobic metabolism, are known to cause the oxidative damage to the cells and the molecules. This in turn is widely accepted as a crucial determinant of both the lifespan and the health span. Denham Hermann invented the free radical theory of aging in the 1950s, which suggested that ROS is formed inside our body from the normal metabolic reactions, thereby causing the aging process. The reason behind this was attributed to an enhanced amount of oxidants in the cellular components. The free radical theory of aging has been also popular by the name of the oxidative stress theory of aging because the oxygen species such as peroxides and aldehydes, which are not free radicals, also harm the cells. When there is an imbalance between the pro-oxidants and the antioxidants, then there is an aggregation of the oxidative damage in various macromolecules with age, resulting in a progressive loss in the functional cellular processes leading to the senescence phase of the cells. The oxidative stress theory of aging has become an important theory to explain the aging at the molecular level. Although there is an ample stock of research over the past 5 decades in context to this theory, almost all the research has shown different correlations. Example, a correlation between enhanced oxidative damage and age, and a correlation between manipulations that enhance the life of cells and a decrease in the oxidative damage and or increase in the power to resist the oxidative damage. The validity of the oxidative stress theory of aging can be tested by determining the changes in the lifespan occurring by changing the level of the oxidative stress. The oxidative stress theory is pictorially given in figure 1. The measurement of oxidation and assessment of the oxidation efficiency can be done by performing a series of chemical tests. These include number 1, determination of the total polyphenol content. Number 2, determination of the total flavon and the flavonol content. Number 3, determination of 2,2-diphenyl 1-picryl hydroxyl phosphate reduction, also commonly known as the DPPH assay. Choice of an antioxidant. Since antioxidants have a very important role to play in the prevention of death of cells, therefore, the choice of the antioxidant as a component of the pharmaceutical cosmetic products is very important. Any antioxidant chosen should be economical, compatible, and less reactive. It should be non-irritant to the skin. It should not cause too much change when added to the cosmetic preparation, thereby maintaining the integrity of the formulation. It should be compatible with a large number of raw materials, thereby giving flexibility of formulation to the formulator. It should be non-toxic. It should be non-corrosive to the packaging materials which are normally used for packing of cosmetics. Its viscosity and temperature curves should be relatively flat. So students, at the end of the module, let us summarize what we have learnt in this module. The stability of a cosmetic formulation depends on the choice of the surfactants, the choice of the humectants, as well as the choice of the antioxidants. Surfactants are characterized by the presence of two different regions in the chemical structure termed the hydrophilic or the water-loving and the hydrophobic or the water-hating regions. The existence of two such regions in a molecule is referred to as amphipathy, and the molecules are known as amphipathic molecules. There are four types of surfactants: cationic, anionic, non-ionic, and amphoteric surfactants. Humectants include those category of substances which are used for moisturizing the skin. Their inclusion as a part of a cosmetic product is important because the drug absorption is reported to be directly proportional to the moisture content of the skin, which is usually 20% by weight. The more the moisture content, the more will be the drug absorption. Humectants are basically an important ingredient of a cosmetic preparation to keep it moist. An antioxidant may be defined as a substance that hinders the oxidation of a given substance. In the process of oxidation, there is a production of ROS or reactive oxygen species, resulting in a continuity of a chemical reaction that finally harms the cell. Some substances have the ability to hinder this and stop this chemical reaction, such as ascorbic acid. There are two types of antioxidants: the endogenous, which are present within our body, and the exogenous, which are not present in the body but however are acquired from the diet. Thank you.